lecture we will look at two things. First of the topic is the time domain manipulations of the signal, and which includes shifting and folding of the signal. And then we will also look at a very important tool which we have covered in analog form for continuous time signals, which is called convolution. But here we will be looking at it for the discrete time signals and systems. Okay, so let's begin the first part, which is the transformation of the independent variable, which in our case is small n. And we will be shifting in time, both positive and negative, that is advance and delay. Similarly, we will be looking at the folding of the signal across y-axis, so in which the values of n for the positive numbers, they move to the other side of the y-axis, and this happens to the negative n-axis as well. And then we will look at the combination of shift and fold, that a signal undergoing the shifting as well as folding at the same time, how that is conducted. So by definition, a signal, if it is given as xn, then it can be shifted in time by changing this n. And for shifting, we change this n to n minus k. This is the default shifting notion, that we change n by n minus k. So if k is positive, that is, for example, k is 3, and we are talking about n minus 3, so k is positive, the signal shifts to its right. What I mean by saying this is that we have fixed the x-axis, fixed the axis, and we will move the signal values to the right or the left depending on what is the value of k. So if k is positive, means the signal xn will become x of n minus k, and the signal will then move to the right, and this is called a delay in the signal. So if k is positive, we mean to indicate that there is a delay in the signal. The signal values which were previously coming at, for example, n equals to 0, they will be delayed and they will occur at some other time, positive value of n. Okay, and if k becomes negative, let's say k equals to minus 3, so n minus minus 3 will become n plus 3. So if k is negative in itself, then the signal shifts to the left, and this is called an advance. Okay, so there are two types of shifts, delay or advance. If k is positive, it's a delay. If k is negative, it's an advance. If the signal moves to the right, it is a delay. If the signal moves to the left, it is an advance. Okay, so now we have a signal xn, and these are the signal values. You can see that origin is at this value 4, and these are the negative values of n, and these are the positive values of n. And we have to find out what will be xn minus 3 and what will be xn plus 2. So as we have seen earlier, that when it is xn minus 3, it means we are talking about a value of k as 3, which is positive. So this means that the signal will be delayed, the signal will move to the right, or the point of origin will move to the left by 3 units. So this is at this point, so 1, 2 and 3. So when we delay the signal, then xn minus 3 will be these same values, but now the origin will be at this one, as highlighted by the pointer. Similarly, when we talk about xn plus 2, it means we are talking about the value of k as minus 2, which means the signal is going to be advanced by 2 units. The signal values will move to the left, and which equally means that the point of origin will move to the right by 2 units. So from here, it will move to 1 and 2 to these points. These are the same things we verbally discussed in the graphical format. You can see that this was the original signal xn. When we delay the signal xn minus 3 by 3 units, the origin, which was at 4, at this point it has moved to 3 units to the left, and now the origin lies here. And for xn plus 2, the original signal xn is now moved to the left by 2 units. So originally the origin was here, but now it has moved, the signal has moved to the left, the origin has moved to the right by 2 units. So xn plus 2 is now having an origin at this sample. We can take the tabular approach as well. It's useful if someone gets confused where the signal would go, and it's a very simple way to do it. So what we do is we write some values for n. We start from you can start from minus 10, minus 9, depending on where the signal values are. So the signal values are from minus 1, which is occurring at minus 5, to we take some cushion value of here, and we take some cushion value here. So we choose some values of n, minus 9 to 7, let's say, and we mark where the 0 is, where the origin is, and then we write the values of xn as minus 5 against minus 1, minus 4 against 0, and so on and so forth. So we write the values of xn against the values of n. Then, because we are interested in finding n minus 3, we select the n minus 3 corresponding to values of n. So minus 9 becomes minus 12, minus 8 becomes minus 11, minus 7 becomes minus 10, and so on. And then corresponding to these values, n minus 3, we write the values of xn minus 3. So we know that for minus 12, minus 11, minus 10, minus 9 till minus 6, the values of xn were 0. So we have all these zeros. And then we see that against minus 5 there was minus 1. So against minus 5 we write minus 1. Against minus 4 there was a 0. So against minus 4 we have a 0. Against minus 3 we had a 1. So against minus 3 we have a 1, and so on. So we fill in the values of the signal against the number of indices where they were occurring, and then we keep track of where the origin was. So origin was against this row. So this indicates that now the new origin for xn minus 3 will occur at this sample. So this is a tabular form of manipulation of this shifting operation. Similarly, if you are interested in finding n plus 2, xn plus 2, then we find out the values of n plus 2 first. So minus 9 will become minus 7, minus 8 will become minus 6, and so on. And against these n plus 2 values, we write xn plus 2 values. So against minus 5, we have seen that there was minus 1. Against minus 4, it was 0, and so on and so forth. But the point to note is that, as indicated earlier, the origin will occur at this value of 4. So this tabular approach comes in handy if one gets confused in how to delay or advance the signal. Now let's move to the folding. The folding is when we change n by minus n in the signal xn, and it is a reflection of the signal about time axis, which is n equals to 0. So for example, we have this same signal xn with these values and the origin occurring at this value of 4. Then if we want to find out x of minus n, then the values get reversed. So the positive values gets to the negative side of n, and the negative side of axis moves to the positive side of axis, just as a reflection occurring along y-axis. So previously the values were minus 1, 0, 1, 2, 3, 4, 4, 4, 4, 4. When we move the signal to x of minus n, then you can see the signal values get reversed. So they start from 4, 4, 4, 4, 4, 3, 2, 1, 0, and minus 1. So the mirror image occurs across the y-axis, which is n equals to 0, and this is what you get when you fold the signal. And this is the similar form of manipulating the folding operation in table form. So you have values of n and values of xn, then you find out minus n, so minus 7 becomes 7, minus 6 becomes 6, and so on. And then we apply we write down the signal values against the origin. So against minus 5 it was minus 1, so against minus 5 we have minus 1, and so on and so forth. So the signal values, you can see they get reversed: 4 4 4 4 4, 3 2 1 0, and minus 1. But folding operation in essence is very simple and can be remembered as a reflection of the signal across origin. Okay, this is where we got to mix the shifting and folding, and you have to pay some attention here. See, this is the time delay operation by k, where xn gets into xn minus k, and this is the folding operation where xn is transformed into x of minus n. The point to remember is that when we delay a signal, then the entire argument, which is n here, is transformed into n minus k. This delay occurs, the impact of delay occurs at the entire argument. But when we fold the signal, then this minus sign is assigned to only n axis. It only affects this n. It does not affect the entire argument. Okay, so if we remember this, that whatever happens in the time delay happens to the entire argument, and whatever happens in the folding only happens on n, then the things which are coming up next will be easier for you to remember. Now what we are going to see is, okay, if we want to mix things up, that is, we want to apply fold and time delay simultaneously, then what happens? So what here are we going to do is, we take the signal xn, we fold it first, and then we apply the time delay signal by